I would like to show you a few corollaries of the inversion formula now. The first one is an example I want to show you. So on the practice class video a little bit later, I'm going to show you that if we have standard Cauchy density, so this is the density function for standard Cauchy. If we have the standard Cauchy density, then the characteristic function, namely the integral from -infinity to infinity exponential itx, and then this density dx, is e to the minus mod of t. So this I'm going to show in a later video. Okay, so now if I want to find out the density, this Cauchy density out of this exponential minus t, then I can use the inversion formula. So the inversion formula told us that we need to, in the absolute continuous case, we need to do the integral of e to the minus itx characteristic function to get the density. So if I do 1 over 2 pi integrate from -infinity to infinity in t, e to the minus itx, e to the minus mod t in t, that will give me back the density fx, which was 1 over pi 1 over 1 plus x square. Okay, that's just a consequence of the inversion formula. So now I want to change course a little bit, and I want to define the Laplace distribution. The Laplace distribution has density, it's a continuous distribution with density e to the minus mod x over 2 for all real numbers. Homework, think about it, this is just a two-sided exponential distribution. So I flip a coin, if it heads I'm looking at an exponential random variable, if it tails I'm looking at minus of an exponential random variable. Figure out that this exactly is the density what you will get from this. I want to find out its characteristic function. So what is the Laplace characteristic function at t? So that's the integral from -infinity to infinity e to the itx times this density, e to the minus x mod over 2 dx. And now if you look carefully above, here and there, you realize that it's actually the same quantity almost. The difference is that here we're integrating with respect to x with a fixed t, whereas up there we integrated with respect to t with a fixed x. So we have to swap the role of x and t. Here we had a 1/2, here we had a 1/2 1 over pi, otherwise it's exactly the same. So exactly the same way as before, what we can find from here is that we have the 1 over pi is not there, so it's 1 over 1 plus, so the difference between these two is the pi factor, which I didn't have here. And also I have to swap the role of x and t, so instead of 1 over 1 plus x square, I just have 1 over 1 plus t square. So that gives me an immediate, fast way of calculating the characteristic function of the Laplace distribution, just by looking at the example of Cauchy. Of course, the first statement, namely that we have exponential minus t for the characteristic function of Cauchy, that will take a little bit of work later on. So that's my first remark. Okay, I have a second remark a little bit further down. So my second remark will be that you can actually do an inversion formula in a slightly different way. And I'm not going to do that. Anybody interested in doing that, you can work out the details. If you want to find out mu of a only, Suppose you are given a characteristic function, you want to find out the probability that x equals to a. So that was just the probability that x equals to a. If x has characteristic function phi, then in a similar way as what we did above, one can end up with this formula. It's the limit of 1 over 2c, integrate from minus c to c, e to the minus ita phi t dt. Okay, that's just an inversion formula for just a single point mass. And that has an interesting corollary, because if x and y are IID and they have characteristic function phi, then let's find out the characteristic function of x minus y. So what is phi of x minus y? So this is the expected value of e to the I t x minus y. X and y are independent, so obviously the exponential is a product. Because of independence, it can be written as the product of the expectations, e to the I t x, and then expectation of e to the minus I t y. Okay. Now, in the first one, of course, we recognize phi of t. In the second one, we recognize phi of t except it's complex conjugated. So in fact, what we end up with is that phi of x minus y is just phi, original phi, mod square, phi times phi complex conjugate. Okay, so now I would like to ask about the probability that these two independent random variables are equal, which is the same as asking about the probability that x minus y is 0. Okay, according to the above, limit c goes to infinity, 1 over 2c, integrate minus c to c, e to the minus it a, but what is a? A is 0, times the characteristic function of x minus y. So I'm going to put the characteristic function of x minus y down here, which is just phi of t absolute value square dt. Okay, now suppose that phi goes to 0. If phi of t mod, or just phi of t, goes to 0 as t goes to infinity, then what happens to this integral? This integral, so e to the it 0 is of course 0, e to the minus it 0 is 1, it 0 is 0, exponential of that is 1. And what we see here is mod of phi square integrated on a length 2c interval divided by 2c. That's called the average value of the function. So that's the average value of phi square. If phi of t goes to 0 as t goes to infinity, then its average value will also go to 0 or minus cc. So in the limit, we get a 0. So then this integral is 0 in the limit divided by 2c. So then the probability that x equals y is equal to 0. Take two independent random variables x and y, but they are never equal to each other. What does that mean? That means it follows that these random variables x or y, they have the same distribution. X has no masses on point, no point masses. It cannot be of positive probability on any single point. Okay, it cannot be discrete in particular, because if it would be positive on some point, then y would also be positive on some point. They are independent, so they could be equal with a positive chance, which is not the case. So just by looking at the decay of phi, you can immediately conclude whether X has point masses. If it decays to 0, then X can't have point masses. Unfortunately, the converse is not true. So if phi doesn't decay to 0, we can't say anything about X having or not point masses.